Two spacecraft reached the edge of the solar system, but only one of them could prove the solar wind really died there. Then why did the first crossing leave room for argument instead of ending the story on the spot? Why did scientists trust Voyager 1, yet still wait years for a cleaner answer? And what did Voyager 2 measure that changed a famous space mystery from almost certain to nearly settled? At first, this sounds like a small difference between two old machines drifting in the dark. One still had a working tool, and one did not. But that missing tool left a hole in the biggest moment of Voyager 1's journey. Subscribe if you want the full trail before the easy version reaches everyone else. Stay close because this story only makes sense when every piece locks into place. The mystery begins with a question that sounds simple enough to answer in one sentence. Where does the sun stop? Most people would say the sun stops at its surface, or maybe at the edge of its light. But the sun reaches much farther than light, heat, and the bright disk we see in the sky. It throws out a stream of charged particles all the time. That stream is called the solar wind. And the solar wind pushes outward in every direction, making a huge bubble around our entire planetary system. That bubble is called the heliosphere. It is not a bubble you can touch, and it is not a hard shell. It is a giant region of space shaped by the sun's particles and magnetic field. Inside it, the sun still controls a lot of the local space weather. Outside it, the wider galaxy pushes back harder. That means the heliosphere is really the far edge of the sun's personal reach. If you want to know where our neighborhood ends, this is the border you have to find. But finding it is not easy. Space does not give us signposts. There is no painted line, no stone gate, no final fence beyond Pluto. There is only plasma, pressure, magnetic fields, and fast particles moving through darkness. Plasma is a gas made of charged particles. It is common in space, but it does not behave like the air in a room. If you want to know where one region ends and another begins, you need instruments, patience, and luck. That is why the Voyagers matter so much. Voyager 1 and Voyager 2 launched in 1977, just 16 days apart. They were built to visit the outer planets during a rare alignment that happens only once in about 176 years. Jupiter, Saturn, Uranus, and Neptune were lined up in a way that let the spacecraft steal speed from each world by gravity assist. That means the planets bent their paths and flung them onward without the probes using much extra fuel. What began as a planetary mission slowly became something bigger. The Voyagers turned into our first deep scouts at the edge of interstellar space. The two craft looked like twins, but they lived very different journeys. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980. A close pass by Saturn's moon Titan sent it above the flat plane of the planets and gave it a faster path outward. Voyager 2 also saw Jupiter in 1979 and Saturn in 1981, but then it kept going. It visited Uranus in 1986 and Neptune in 1989, the only spacecraft ever to do that. Those extra stops made Voyager 2 slower, but they also shaped the strange twist at the heart of this story. Because while Voyager 1 raced ahead, Voyager 2 kept one tool alive for a moment still decades away. Now we have to talk about that tool. Both spacecraft carried a plasma science experiment. Its job was to measure the plasma flowing around the craft. In plain words, it could test the wind in space. It could tell scientists the speed of the solar wind, the density of the plasma, and how hot that thin, charged gas was. The instrument used devices called Faraday cups, which collect charged particles and help measure their motion. That may sound technical, but the basic point is simple. It let the spacecraft feel what kind of invisible river it was moving through. That river mattered because the border of the heliosphere is defined by change. Inside the sun's bubble, the solar wind moves outward. Outside the bubble, local interstellar plasma is denser and behaves differently. At some point, the outward solar wind has to lose the fight. The place where the solar wind is stopped by pressure from interstellar space is called the heliopause. That is the true edge in this story. Cross it, and the sun's moving bubble is behind you. Stay inside it, and you are still in the sun's weather system. Here's where the first crack appeared. Voyager 1, the faster craft, was supposed to reach that border first, and it did, but the plasma instrument on Voyager 1 stopped working back in 1980, long before the craft reached the outer edge of the heliosphere. That meant when the great moment finally arrived, the instrument best suited to detect a full stop in the solar wind was silent. Scientists could still study the crossing, but one of their most direct ways to test it was gone. The spacecraft could not simply say, "The wind has ended here." Think about the timing of that failure. An instrument built to test plasma survives the giant planet mission, then dies more than 30 years before the exact event where that reading would matter most. It is almost cruel. Voyager 1 kept going and kept sending other kinds of data, but the one tool that could have settled later debate in the clearest possible way had already fallen quiet. So when Voyager 1 reached the outer border in 2012, scientists were watching a drama unfold with one key witness missing, and that missing witness changed the tone of the whole discovery. Voyager 1's clues were still dramatic. In August 2012, the spacecraft saw a sharp drop in particles that came from inside the heliosphere. At the same time, it saw a rise in galactic cosmic rays, fast particles coming from beyond our solar system. That looked exactly like what scientists expected near the edge of the sun's protective bubble. If particles from the sun fell and particles from the galaxy rose, the shield around the spacecraft seemed to be fading. To many researchers, this strongly suggested Voyager 1 had entered interstellar space, but strong suggestion is not the same as a direct plasma reading. Then came the part that made the story harder. Some scientists expected the magnetic field direction to change a lot once Voyager 1 crossed the heliopause. Instead, the field beyond the border did not swing in some dramatic new direction. It stayed oddly similar to the field inside. That was strange. It did not prove Voyager 1 had failed to cross, but it kept the door open for questions. Was the craft truly outside the heliosphere, or sitting in some messy transition zone where old and new conditions mixed together? That doubt did not stop the mission team from building a strong case. They had another clue, and this one was clever. After solar eruptions from the sun passed through the region around Voyager 1, they stirred the thin plasma there. Those disturbances made the electrons in the plasma wiggle and create radio waves. By measuring the frequency of those waves, scientists could infer the density of the plasma around the spacecraft. The result suggested a much denser environment than the one inside the heliosphere. That is exactly what scientists expected outside the sun's bubble. So the case for a crossing grew stronger. Still, notice what happened. The best evidence for Voyager 1's new environment became indirect evidence. Scientists were not measuring the solar wind flow directly with the plasma instrument. They were reading the behavior of radio waves and using that to infer density. That is smart science, and it worked. But it also meant the famous claim that Voyager 1 had entered interstellar space rested on a chain of reasoning instead of on a clean, direct reading from the missing tool. For many people, that was enough. For others, the story still felt slightly unfinished. And that unfinished feeling matters. This was not some side note in a minor project. This was the first human-made object ever said to have crossed into interstellar space. If there was ever a moment when scientists wanted every major instrument working, this was it. Instead, the crossing became real, historic, and a little uncomfortable at the same time. The mission team was confident, yet the wider public kept hearing a version of the same question. If Voyager 1 really left the heliosphere, why did it still sound like people were explaining around a missing answer? That question sat there for years. Now pause on that doubt for a second. If you had to decide with one major instrument gone, would you have called Voyager 1's crossing settled, or would you have waited for one cleaner measurement? Leave your call in the comments before we move on, because the next stage is where the old argument meets its hardest test. Voyager 2 was still coming. It was slower because of its longer route past Uranus and Neptune, but unlike Voyager 1, it still had a working plasma instrument. That changed everything. It meant the second crossing could answer the exact question the first crossing could not answer directly. When Voyager 2 reached the edge, scientists would finally be able to measure whether the solar wind around the craft had really dropped to zero. No indirect chain would be needed for that part. The missing witness from Voyager 1 would speak through Voyager 2. By 2018, Voyager 2 was about 11 billion miles from Earth, or around 18 billion kilometers. That is so far away that a radio signal needed about 16.5 hours to travel one way between the spacecraft and Earth. Even at that distance, the old probe was still sending useful data, and in late August 2018, the first signs of change appeared. Voyager 2's cosmic ray subsystem saw an increase in galactic cosmic rays hitting the spacecraft. That looked familiar. It was one of the same clues Voyager 1 had seen before its own crossing. The border seemed close. Then the tension rose fast. On November 5, 2018, one instrument detected a sharp drop in energetic particles from the sun. That was another strong sign that the spacecraft was leaving the heliosphere behind. But this time, the story did not have to stop at particles rising and falling. This time, the plasma instrument was alive, and on that same day, it watched the speed of the solar wind decline. Then it saw something far more important. It saw the outward solar wind flow fall to zero around Voyager 2. That single result is the heart of the mystery. Voyager 2 directly measured something Voyager 1 never could. It measured the stop. Not a hint of a stop, not a stop inferred later from radio waves, but a direct loss of outward solar wind flow at the boundary. Once that happened, the meaning of the crossing became much clearer. The spacecraft was no longer simply in a region where outside particles were getting stronger. It was in a region where the sun's own wind was no longer flowing past it. That is why the result mattered so much. In simple everyday language, Voyager 2 had been riding in the sun's invisible wind for more than 40 years. Then, at the edge, that wind vanished. Imagine sailing down a river your whole life and then entering water where the current you have always known suddenly stops. You would know you had reached a different place. That is what the plasma instrument gave scientists. A direct feel for the local current. And the local current said the sun's outward flow had ended there. That was the clean reading Voyager 1 did not have. Now here comes the part that makes the answer even stronger. Voyager 2 did not just repeat the same broad pattern as Voyager 1. It crossed the heliopause in a different place and at a different time in the sun's activity cycle. Voyager 1 crossed in August 2012 at about 121.6 astronomical units from the sun. Voyager 2 crossed in November 2018 at about 119 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, about 93 million miles. So both crossings happened more than 100 times farther out than Earth, and yet they happened at distances surprisingly close to each other. That closeness was a clue of its own. Scientists had expected the heliopause to move in and out as the Sun went through its roughly 11-year activity cycle. During busier times, the sun can push its bubble outward. During quieter times, the bubble can shrink. The two Voyagers also crossed in different directions, not on the same path. So a big difference in crossing distance would not have been shocking. Instead, the edge appeared at nearly similar distances for both spacecraft. That suggested the shape and motion of the heliosphere might be more balanced or more complicated than some simple models predicted. But the plasma reading from Voyager 2 did more than settle an old argument. It opened new ones. Scientists expected interstellar plasma beyond the heliopause to be denser than the plasma inside the heliosphere. Voyager 2 confirmed that general idea, yet it also found that the plasma just beyond the heliopause seemed warmer than many had expected. Measurements suggested temperatures around 30,000 to 50,000 Kelvin. Those numbers sound absurdly hot. But space plasma is so thin that high temperature does not feel like standing near fire. It means the particles carry a lot of energy, not that the region would roast a human body like an oven. Why did that matter? Because models and earlier expectations had often pointed to lower values for nearby interstellar plasma. So when Voyager 2 reported higher temperatures, the results suggested the boundary region was not calm. Something seemed to be squeezing or disturbing the plasma there. One likely answer was compression. As the interstellar medium pressed against the heliosphere, the plasma near the border may have been heated by that pressure. In other words, the edge of the sun's bubble did not behave like a quiet meeting line. It behaved like a stressed frontier. Voyager 2 also saw signs that plasma density increased slightly just before the crossing. That matters because it suggests particles were bunching up near the inner side of the heliopause. The flow from the sun was being slowed and compressed before it finally reached the boundary. Picture traffic thickening before a blocked road. The cars are still moving, but they are crowding together because something ahead is stopping the easy flow. That seems to be part of what the plasma instrument saw. And it told scientists the heliopause is not just one magical instant in space. It has a surrounding region where conditions grow tense. So far, the case sounds stronger and cleaner for Voyager 2 than it ever was for Voyager 1. But then another strange clue returned from the dark. The magnetic field beyond the heliopause looked oddly aligned again. Voyager 1 had already hinted that the magnetic field just outside the heliosphere ran almost parallel to the field just inside. Some people wondered if that first result had been a local fluke. Voyager 2 crossed in another place, years later, and still found a similar alignment. That made the strange pattern harder to dismiss. Two crossings now pointed to the same surprise. Before I tell you what that does to the bigger picture, make your guess. When two spacecraft cross the same border in different places and still see the outside magnetic field lined up with the inside one, what does that suggest to you? Write your prediction below, because the answer makes the border feel less like a wall and more like a living thing. If both Voyagers saw nearly aligned magnetic fields across the boundary, then the old clean picture of the heliopause gets weaker. The border is real, but it is not simple. It is not a hard shell that forces every property of space to flip at once in a dramatic way. Some features change fast. Some seem to carry through or bend more gently. That tells us the sun's bubble interacts with interstellar space in a more tangled way than many early sketches showed. The heliopause marks a crossing, yes, but it also sits inside a messy relationship. And there was another twist. Data from Voyager 2 suggested that some particles from inside the heliosphere may leak across the heliopause. That is a big deal. A shield that protects Earth from much of the galaxy's radiation may not be perfectly sealed. It still blocks a huge share of incoming cosmic rays. NASA has said the heliosphere protects the planets from more than 70% of some of that radiation. But protection is not the same as perfect separation. Voyager 2 hinted that the border can be porous, at least in places. That means the sun's domain may breathe, mix, and leak along the edges. Even the location of the crossing may matter. Voyager 1 passed through a part of the heliosphere nearer the front, the side facing the oncoming flow of interstellar space as the sun moves through the galaxy. Voyager 2 crossed farther around the side, often called a flank. Scientists think the flank may be more porous than the nose region. If that is true, then the edge of the heliosphere may not behave the same way everywhere. Some regions could be tighter, some could allow more particle exchange. That gives the border a personality, almost like a coastline with cliffs in one place and inlets in another. Now think about what Voyager 2 really gave us. It did not just validate Voyager 1. It gave us a second sample in another region of the heliosphere. That is vital in science. One measurement can always be odd. Two similar measurements in different conditions begin to reveal a pattern. Voyager 2 showed that the particle changes seen by Voyager 1 were not just a local accident. It showed that magnetic field alignment beyond the heliopause was not just a strange one-off event. And most importantly, it supplied the direct plasma reading that turned the stopping of the solar wind from an argument into an observed fact. That is why the phrase, "measured something Voyager 1 never could," is not just dramatic wording. It is literally true in the most important sense. Voyager 1 could infer density outside the heliosphere by listening to plasma wave behavior after solar eruptions passed through. That was powerful and persuasive. But Voyager 1 could not directly measure the speed of the solar wind at the crossing because its plasma science experiment had died in 1980. Voyager 2 still could. And in 2018, it used that ability at exactly the right moment. That difference changed the confidence people felt about the border. The story becomes even richer when we step back and ask why the instruments survived differently. There was nothing mystical about it. Spacecraft age unevenly. Different paths expose them to different conditions. Power systems weaken, parts fail, and some tools last longer than anyone dares hope. In Voyager 2's case, the plasma instrument stayed alive for more than 4 decades. That is extraordinary. A machine built in the 1970s kept working long enough to settle part of a space debate that did not fully form until the 21st century. It was like an old witness surviving just long enough to answer one decisive question. And then, after doing that job, the instrument reached its end. In 2024, NASA shut down Voyager 2's plasma science instrument to save the spacecraft's shrinking power supply. That sounds sad, and it is, but there is something almost perfect about the timing. The instrument did not fail before the great moment, the way Voyager 1's had. It stayed alive long enough to cross the heliopause, measure the stop in the solar wind, help estimate the temperature and density in the new region, and confirm that the second crossing carried the same broad signature as the first. Then, only after history was made, it finally fell silent. That ending gives the instrument a strange dignity. It performed the one task only it could perform, then it bowed out. At that point, Voyager 2 still had other instruments working, including tools that measure magnetic fields and energetic particles. So the spacecraft did not go blind. But the unique era of direct plasma readings from that old instrument was over. The key point is that it had already delivered the piece no one can replace now. No new command from Earth could ask Voyager 1 to redo its missing measurement. Voyager 2 had done it for both of them. This is the moment where the tone of the story changes. Up to now, we have been building toward a clearer answer about the past. Did Voyager 1 really cross into interstellar space in 2012? Voyager 2 says yes, almost certainly yes, because it saw the same kind of transition and also measured the direct stop in solar wind flow during its own crossing in 2018. But once that question becomes clearer, a new one grows larger. What exactly is the heliopause if it can be real, measurable, compressed, warm, and still not behave like the simple border we once imagined? That question is still open. Scientists now think both Voyagers may still be in a disturbed region just beyond the heliosphere, rather than in perfectly undisturbed local interstellar space. That idea matters. It means crossing the heliopause does not instantly place a spacecraft into a calm and fully separate galactic environment. The sun's influence can still leave a stirred-up zone beyond the formal border. The interstellar medium itself may also be responding to the pressure of the heliosphere. So the edge is not only a dividing line, it is a zone of interaction, and we are still learning how thick, active, and variable that zone really is. That unfinished part of the story is why Voyager 2's success did not end all mystery. It narrowed the mystery. It cleaned up one of the biggest doubts. But it also showed that the real shape of the border is more complex than a simple schoolbook picture. The heliosphere may expand and contract with the solar cycle. Its flank may be leakier than its front. Plasma may compress on both sides. Magnetic fields may line up more than expected. Each answer sharpens the map, and each new sharp edge reveals more texture. If you had to picture it now, do not picture a soap bubble floating untouched in empty darkness. Picture a moving bubble of solar influence pressing through the galaxy. Picture the outer skin under stress, shaped by outside flow, bent by magnetic fields, and thin enough in places to let particles trade sides. That is a harder image to draw, but it is closer to what the Voyagers are telling us. And because Voyager 2 had the instrument Voyager 1 lacked, we can say that with much more confidence than before. The second crossing did not replace the first. It completed the first in a more direct language. Before we go to the final verdict, stop here and make one more call. Do you think the real lesson is that the heliosphere is stronger than we imagined, or that it is stranger and leakier than we hoped? Put your answer in the comments now, because the verdict depends on how you weigh protection against complexity. Here is the fairest verdict we can build from all the pieces. Voyager 1 almost certainly became the first human-made object to enter interstellar space in August 2012. Its particle readings and later plasma wave evidence made a strong case. But because its plasma instrument had failed back in 1980, it could not directly measure the solar wind stopping at the crossing. That left a gap, and that gap gave the mystery room to breathe. Voyager 2 crossed the heliopause in November 2018 with its plasma instrument still alive. It directly measured the solar wind drop to zero. That is what Voyager 1 never could do. So was the bold opening claim true? Yes, but only if we say it carefully. Voyager 2 proved that at the heliopause, the outward solar wind around the spacecraft had ended. That direct measurement made the nature of the crossing far harder to dispute. It did not mean every feature of the border suddenly became simple. The magnetic field still behaved in a surprising way. The plasma outside seemed warmer than expected. The boundary looked compressed, active, and maybe a little porous. Voyager 2 confirms the crossing and complicated the border at the same time. That is why this story matters beyond one line in a history book. The heliosphere is not just a distant science object. It is the giant shield that helps protect Earth and the other planets from a large share of harmful galactic radiation. If we want to understand how well that shield works, how it changes over time, and what lies beyond it, we need to understand its edge. Voyager 2 gave us the clearest direct touch of that edge we have ever had. And because Voyager 1 went first, the second crossing also acted like a check on the first one. Together, the two missions tell a stronger truth than either could alone. There is also something deeply human in all this. We did not solve the mystery with perfect tools at the perfect time. We solved it with two aging machines launched in 1977, one missing a key instrument, the other still holding on long after anyone expected it to. We solved it slowly. We solved it with debate, patience, and a stream of tiny radio signals crossing billions of miles of darkness. That is often how real discovery works, not as one clean shout, but as years of doubt closing inch by inch until the picture finally sharpens. And that picture reaches back to us. The place where the sun's wind stops may seem far from daily life, but it tells us where our home's outer weather finally gives way to the galaxy. It tells us what stands between Earth and a harsher cosmic environment. It tells us what any future deep mission will have to pass through on its way outward. When Voyager 2 measured the solar wind dropping to zero, it was not just solving a technical argument. It was drawing a truer line around the space we live in. That makes the result feel personal, even from billions of miles away. There is one more reason this direct reading mattered so much to scientists on Earth. Space physics is full of models, and models can look convincing until nature gives a clear check. Voyager 2 became that check. It told researchers that some parts of their picture were solid, like the sharp drop in solar particles and the rise in outside cosmic rays. But it also told them other parts were too neat, especially the idea of a simple border with a dramatic magnetic turn. That kind of correction is priceless because it keeps theory tied to reality instead of beauty. And there is a final irony that is easy to miss. The slower spacecraft became the clearer witness. Voyager 1 got to the border first and made history. Voyager 2 arrived later and made that history easier to trust. That is rare in science. The first discovery usually gets the fame, but the second one often tells us what the first one really meant. Without Voyager 2, the story would still feel unfinished. Because of Voyager 2, the edge feels strange but not invisible now. So if you take one thing from this story, let it be this. Voyager 1 found the edge first, but Voyager 2 measured the missing fact that made the edge harder to deny. The first craft opened the door, the second tested the floor beneath our feet. Together they showed that our solar system does have a real border in the flow of plasma, yet that border is alive with pressure, heat, leaks, and magnetic puzzles. The answer became clearer, and the frontier became stranger. That is the kind of truth space gives us most often. If you want more investigations that go past the simple headline, subscribe and turn on notifications so you catch the next one early. Then tell me in the comments which matters more to you here, the proof that the solar wind stops, or the mystery of why the border behaves so strangely. And share this with someone who loves space stories where the final answer raises an even bigger question. Thanks for staying with me all the way to the edge tonight.